Hello. So we are going to be going over topic 1.3 today, and this involves estimating limit values from graphs. And we have our something to think about, and that is reasoning with definitions, theorems, and properties can be used to justify claims about limits. So we're going to be learning about all those definitions and theorems and properties. The learning objective is to be able to estimate limits of functions. So we're estimating limits based off of functions, based off of graphs, tables, all those different ways. So um, one thing that we need to talk about here is what one-sided limits are. So we've talked very briefly already about finding the limit, and so we know that it's the value that the function is approaching. However, the function may not always be approaching the same value from both directions. So we have one-sided limits to be able to talk about the different sides and the approaches and their approaches. So we have our notation here. The limit as x approaches a from the left side. That's what this is saying here. This little negative sign that looks like an exponent, that's telling us it's a left-handed limit. And so we can see in the picture here, if this is our a value here, that's our x. So as this function has x values approaching a, then we follow the graph from the left side, and we can find this limit, which in this case is capital L, whatever that y value is. And we can look at the other side of it. The notation here, the limit as x approaches a from the right side, is written with a plus as the exponent. So we have the limit as x approaches a from the right of the function f of x is equal to L. And we can see that in the graph here. Our a is down here, and so we're following the x values from the right side and seeing what that value is once we hit x equal to a there. So let's talk about our first theorem here. So our theorem states that the limit as x approaches a, and a is some x value, of f of x is equal to L, so L is some y value, if and only if the limit as x approaches a from the right side of f of x is equal to the limit as x approaches a from the left side of f of x. So what that means is we need to have a function that from both directions leads to the same value, which in this case we call L. Something like this, for example, say this is A. That limit does not exist because if you look at the left-hand limit compared to the right-hand limit, they have different values. So that would mean that they're not equal in that example. Therefore, the limit as x approaches a does not exist. Now, this is not to say that the limit from the left doesn't exist, because we can see here that the limit from the left is whatever y value this is, and the limit from the right exists. We can see here it's whatever this value is. However, the total limit, so as we approach this a value from both sides, the limit does not exist. And we have our little Lindsay Lohan there, Mean Girls movie. Gotta love it. So let's look at an example. We have the function f of x is equal to 1 over x. And it states here that the limit as x approaches 0 of 1 over x does not exist. So we're going to graph this out and try to analyze it and see what's going on. Now, 1 over x is a parent function. So You should be envisioning it right now. You should know what it looks like. This is very important. If you don't know what it looks like, you're going to find out in a second and you're going to memorize it. So, very rough sketch. There it is. That is 1 divided by x, our function there. So we have two asymptotes. We have the vertical asymptote at x equal to 0, and we have the horizontal asymptote at y equal to 0. So that means this function is kind of just going off in either direction there. So we need to talk about what is the limit as x approaches 0. And what we're going to do is we're going to look at both sides and talk about what's going on each side there. So I'm going to write this out, and then that's going to lead us to the limit as x approaches 0 of our function. So let's start with the left side. I'm going to start way over here and just kind of follow the function. And I'm trying to get close to x equal to 0, which is this line right here, that's x equal to 0. So I'm moving in towards it, but notice, what is my graph doing? The more and more I try to get closer to x equal to 0, my y values, they're going down, right? Are they approaching any specific y value? Not really, right? They're actually approaching negative infinity from the left side, because it's just going down very quickly, I might add. Now let's look at the right side. So I'm going to start way off to the right, and I'm trying to approach x equal to 0. And again, what are my y values doing this time? Closer and closer my x values get to 0, those y values, they're shooting up. So they're all headed towards infinity. So if my left side is headed towards negative infinity, my right side is headed towards positive infinity, what is going on with this total limit? What is the limit as x goes to 0? Well, there is no limit. The limit does not exist because they're going crazy. They're going off in different directions. So there's no limit happening when x is equal to 0. So what we say, instead of writing out the limit does not exist every single time, we say DNE, does not exist. Let's look at another example. It says, sketch the graph of f of x equal to the square root of x minus 3 and find the following if possible. So a lot of these questions tell you to sketch the graphs. This means you need to be sharp on your parent functions and your transformations, okay? So the parent function here is the square root of x, and the transformation we have inside of the function x minus 3. So that means we have the square root of x function, which, think about what it looks like. Do you have it? Do you know? You know it? Goes like that, right? Square root of x, but it's shifted to the right by 3. So my graph, again, a little rough sketch here, but just so we can get an idea of what it looks like, is going to look like that. There is the square root of x minus 3. So it's really important, if you don't know your parent functions, you can't think of them off the top of your head, I'm going to share a little Quizlet on parent functions and make sure that you study that, because it's really important that you just know it. Gotta just know it. All right. So we've got the graph. Now let's talk about the limits. So the limit as x approaches 3 from the right, that's how we would read this first part here. The limit as x approaches 3 from the right. So 3 is right here. Okay. And I've drawn my function. So I'm going to follow the path of my function from the right side and approaching 3. And where does my y value end? It ends at y equal to 0. So this tells me that my limit as x approaches 0 from the right of the function, I can either write f of x, or I can, since I know what f of x is equal to, it's equal to x minus 3. I can write that there. I know that's going to equal 0 because that's the direction it's headed towards. The next part asks the limit as x approaches 0 from the left side. Now I'm going to write f of x there. Okay, so I've got 3. Again, I know it's there. Now I want to trace the graph on the left side of the graph, but guess what? There's nothing over here. There's no graph to the left of 3. So what is the limit? Does not exist. There can't be a limit if there's no function. Am I right? Right. So if there's no function that exists in that area to the left of 3, then, oh, sorry, I keep writing 0. Oops. Sorry, the question is 3 from the right and 3 from the left. Sorry. Okay. Now the last part, the limit as x goes to 3 of f of x. Let's just write f of x. So here's where the two are going to come together. Now, if the limit as x goes to 3 from the right is 0, and the limit as x goes to 3 from the left does not exist, they are not the same, then our limit as x approaches 3 in total does not exist. So how could we make this exist? Well, I mean, in this case, we would have to change the function so that we can create a function that actually has a left side and that actually meets up at y equal to 0 there. That's the only way that we can make this limit exist. Otherwise, the limit does not exist. All right, this next one here, the graph of f of x equal to the absolute value of x divided by x. This is a tricky little function that comes up very often. So pay close attention here as to what the graph looks like and where it comes from. Before we can graph it, we got to think about absolute value of x. So the absolute value of x is a function that is actually a piecewise function. Because if you graph it out, this is what the graph of the absolute value function looks like. And it's really just a combination of two lines. So the first line is x when x is greater than 0, or we can say equal to, right, technically. So that's this kind of right side of the absolute value function. And then it's a line on the other side, but this is the line with a negative slope. So this is negative x for all of x that is less than 0. So if we are trying to graph the function that is the absolute value of x divided by x, it's actually going to be this same absolute value, but we want to divide this all by x. So technically, x divided by x gives us 1. And then negative x divided by x is negative 1. And this is for all of x greater than 0, all of x less than 0. So I can go ahead and now graph this. And this is going to look like, let me center this a little bit better there. This is positive 1, this is negative 1. So for all the values of x that are greater than 0, I'm going to have a me do a different color. Horizontal line. That stops right there. And then for all the x's that are less than 0, a horizontal line along -1. So this is our graph of the absolute value of x divided by x. Okay. Now we've got the graph. Now let's talk about the limits. So the first one is the limit as x goes to 0 from the left of our function f of x, or absolute value of x over x. So I'm going to just follow the graph. From the left side, I see that it's approaching -1. So I'm going to say that my limit from the left is -1. Now the limit as x approaches 0 from the right side of our function here, I'm going to follow the path of the function from the right to x equal to 0, and that has a y value of 1. So now from the left side, my limit is -1. From the right side, my limit is +1. So what is my limit as x approaches 0 in total? Well, if the limit from the left is one value, the limit from the right is a different value, then the limit does not exist. Okay. And we got a couple more here. We're going to go through these a little more quickly. So the limit as x approaches 1 of f of x. That means we need to check both sides. We need to check the left side, and we need to check the right side in order to determine what that total limit is going to be. So x equal to 1 is right here. And from the left side, if I follow the graph, it leads me to 0. So I know that the limit from the left is going to be 0. But the limit from the right, as I move in towards x equal to 1, my limit is 1. So my limit as x goes to 1 of f of x does not exist, since we have two different values from the left and the right. Now let's try the limit as x approaches 2. There's my x value. We've got to check the limit as x approaches 2 from the left. And then we've got to check the limit as x approaches 2 from the right. Oh, why did I write 0? So if I follow it from the left side, as I reach 2, I can see, you probably can't see when you zoom in, I can see there that this value is y equal to 1. So I can say that the limit from the left is 1, but then the limit from the right, as I follow the graph and move in towards 2, it's y equal to 1. So the limit from the left is equal to the limit from the right. So that tells me that the limit as x approaches 2 of f of x is equal to 1. Since both sides meet at 1. And lastly, here we have x, the limit as x approaches 3. So 3 is right over here. And we have the limit as x approaches 3 from the left, the limit as x approaches 3 from the right. And looking at the graph, I actually see pretty quickly here. From the left, it's leading us up to y equal to 2. And from the right, it is also leading us up to y equal to 2. So since both sides are 2, my limit as x approaches 3 of the function f of x is 2. Okay, we've got some piecewise functions for the next two problems. So we're defining f as this piecewise, and we want to determine what is the limit of f of x as x approaches 2. So what is the limit of f of x as x approaches 2? So in order to do that, we need to figure out what is happening to the left and to the right of 2. And piecewise functions lend themselves to determining this pretty quickly. So if we look at the piecewise function, what we're really going to be focusing on is this side right here. And so when x is equal to 2, I see that there's a point at 1. So because I'm looking for the limit as x approaches 2, I actually don't really care what's happening when x is equal to 2. It doesn't make a difference to me. I want to know what's happening to the left of 2 and what's happening to the right of 2. So if I want to check the left side, I want to look at the conditions that are all to the left of 2. So these are x values from -2 to +2, but not including 2. So those are all to the left. So when that's the case, I'm looking at the graph of x squared. So in order to find the y value at x equal to 2 of x squared, I'm just going to plug it in. And so I get 4 in this case. So this means that my limit as x approaches 2 from the left is equal to 4. Now from the right side, I'm going to look at this side here. That's all the x values that are greater than 2. And what I see is that all of the values are going to be 5. Everything to the right of 2 is going to equal 5. So I'm going to say the limit here is 5. Well, if the limit from the left is 4 and the limit from the right is 5, then that means my total limit does not exist. And if you need a little kind of guidance in visualizing this, we can do a quick little sketch here. So we've got the point 1, 2, and then we have x squared for all the values to the left, 2, 4, all the way from -2, looks something like this. And then we have 5 for everything greater than 2. So that's what that piecewise function looks like. And so you can see visually the left and the right don't match up. So the limit does not exist in this case. All right, and here's our last one, very similar to the one that we just did. So we're trying to find the limit as x approaches 1 of f of x. And our f of x is this piecewise function. Again, we've got this piece that tells us there's a point at x equal to 1. Remember, we don't really care what's happening exactly at x equal to 1. We want to know the limit as we're approaching 1. So from the left side, we're approaching 1 with the function -x cubed. So what I'll do is I'll do direct substitution and plug in 1 to this function. And that's going to give me -1. So I know that from the left side, as x is approaching 1 from the left side, our value is -1. And as x is approaching 1 from the right side, I'm going to check this condition down here and do my direct substitution. So I'm going to plug 1 in, and that gives me -2. Because those two limits are different, that means my function does not exist. So there was a lot of do not exists in this section here, and that's really to drill in the theorem that says that the limit from the left and the limit from the right have to equal each other in order for the limit to exist. We'll get into what it means to be continuous in our lesson coming soon, but that is our theorem that's all about whether a limit exists or does not exist.